In this last section, we're going to just tie up loose ends dealing with limits and talk a little bit more about graphs and limits. In the previous section, we already looked at the notation for left and right-handed limits. Our textbook introduces it in this section, but I thought it was better that we did it in the previous section. It'll make this section go a little bit quicker. So aside from a few loose ends, we're going to look at one other concept in this section called continuity. You already know a bit about it, but we're going to kind of explore its relationship to limits. So here's a function, f of x. We know the limit doesn't exist because the left and right hand limits are not in agreement. From the left, at the limit as x approaches 3 from the left, as we squeeze in from the left-hand side towards 3, your function is heading up towards that height of 2. As we squeeze in from the other side on 3, our functional values are heading down towards that height of 4. So the limit doesn't exist because these are not in agreement. And the behavior I want to look at in this section is this jump. We refer to it as a discontinuity. In fact, we call this one in particular a jump discontinuity, but we'll get to that below. So this is the notation that really gets introduced at the beginning of section 1.6 in your text, but you've already seen it, which is good. I put example 1 in here pretty much as a reminder to me to make sure you know where to find absolute value on your calculator if needed. Certainly you don't need the absolute value if you wanted to find the absolute value of -5 or something. But if you wanted to graph a function like f of x equals the absolute value of x minus 4 over x minus 4, you have to know where it is on your calculator. So if you press the math button, it's on the TI-84 series of calculators, it's right below the alpha button. It just has math. It's should be pretty easy to remember. It'll bring up a menu that has a number of columns. Just right arrow to the second column, which is number, and it's the first one on the list, ABS. So when you graph this, you would have y1. You need to be in the y equals screen where you enter functions to be graphed, and you'll hit the ABS button. It'll open parentheses. You'll put x minus 4. Make sure you close parentheses, and then the denominator also make sure it's in parentheses as well. If you don't get a graph that looks like the one over here, then you'll know something is entered wrong. One difference is when you do graph this on the calculator, it's not showing you the whole story. At 4, it'll look like this on your calculator. Okay, but it's not defined at 4. We know this because the denominator would be 0 if x were 4. So x can't be 4. So those should be both open circles there. Even if they were closed, it wouldn't be a function, but that wouldn't really affect what's going on with limits if one was closed and one was open, but they are both open. So just looking at this graph, you can tell this limit does not exist, since the limit as x approaches 4 from the left of our function f of x, well, what's that? As we squeeze in from the left-hand side towards 4, your function stays at a height of -1. And the limit as x approaches 4 from the right-hand side, and remember, we're just asking what height does your function head towards as x approaches 4 from the right. So as we squeeze in from the right-hand side, all the functional values are basically staying at a height of 1. And since those are not equal, our original limit does not exist. So I really just put this in here to make sure I remembered to remind you or tell you where the absolute value is on your calculator, in case you didn't know. So it's easy to find. Math button, it's the second column and it's the first one on the list. So this thing here and the thing that showed up on the graph at the top of the page is what we call a jump discontinuity. There's a vertical jump in the graph. This will happen anytime the left and right hand limits are different. So this idea of continuity is is really the only new thing in this section, since we've already seen the left and right hand limit notation. But a function will be continuous at a value if the limit of the function and the actual functional value are equal. Okay, so for a function to have a limit that was the same, you'd have to have something like this, so that the function's heading to the same height from either side. It'll be continuous if the function's also defined to be the same height. So this is how we've always described polynomials to you. You could draw them without ever lifting your pencil. So all the function heights and the limit heights are the same, and that's continuity. This will be a prerequisite for pretty much everything we do in this course, and the reason is, in order for me to draw a tangent line, we talked about in the very, very first intro video that one of our goals is to define the slope of a curve. The curve's got to be defined there, and we have to be able to draw a tangent line. So this is continuity. It's a limit definition. It's really easy looking at a picture, but I wanted to draw the different types of continuities, or discontinuities, sorry. The good thing is pretty much every function you've ever studied or ever will study is at least continuous on its domain. So things like polynomials, rational functions, roots, exponentials, logs. It's not part of this course, but trigonometric functions, sums, differences, products, quotients, and multiples of all these are also continuous on their domains. So mostly for us, this will be a domain issue. So the different types of discontinuities are removable, jump, and infinite. I include a fourth called a gap discontinuity, because I think it's a little bit different than the jump discontinuity. A lot of books include the gap with the jump, which I don't think is accurate. So a removable discontinuity is something like this, where there's just a hole in the graph. Okay, we call it removable because when in the last section, when you were doing the algebra and you've had a common factor in the top and bottom of a fraction, when you divided and then were able to take the limit, you removed the discontinuity. Also, I could easily define a new function that just filled in that one hole without changing the overall look. Jump discontinuity you just saw. That's the interesting one, where the left and right hand limits are different. And one of these could be defined. And likewise back here, your function could be defined. The limit could exist, but since they're not equal, there's a break in the graph, an interruption. Here, the function's defined, but the left and right hand limits are different. So this is a jump, and it's a vertical jump. An infinite discontinuity is one where you have something with asymptotic behavior. So even though in this case we would say the limit was positive infinity, there's still clearly a discontinuity. We're jumping across that asymptote. A gap discontinuity, like I said, is often included with the jump discontinuity, but it's more of a horizontal jump, so I like to think of it differently. This would be something like this, where there's a gap in the domain, a horizontal gap. Just has a different look than the jump discontinuity, which is more of a vertical jump. This is like a horizontal jump. So often textbooks will include those together, but those are the four basic types. Notice looking at a graph, it's pretty easy to tell whether you're discontinuous or not. You either lifted your pencil or you didn't to continue drawing the graph. So these are the 4 examples where things would fail. If you look everywhere else, aside from these values where we're discontinuous, this one again is a little bit different. This is continuous where it's defined. So is this. So are these pieces. It's just that one location where there's an issue. Here there's lots of issues in between because there's an entire gap in the domain. So those are the 4 basic types. Let me clean this up again. And like I said, on the removable discontinuity, you can still be defined, just not at the same height. And these could both be open or one could be closed. And for the infinite discontinuity, we could even have the scenario where, and I think we had a graph similar to this in the last section, where we were only asymptotic on one side, and then we had, a curve over here. In this case, the function's defined, but the limit still doesn't exist. And we would still call it say a left-sided discontinuity. Sometimes books talk about left and right discontinuous. Not something we really need to pay much attention to. But looking at the jump discontinuity here, this we would call left continuous because it's defined. I wouldn't even sweat that. I can't remember if our text mentions that. If they do, you'd probably pass over it because it's probably just one sentence, not a big deal. So function's continuous if the functional values are the same as the limit values. Okay, so the function's defined. That means C is in the domain. This one's more loaded. This one means that the left and right hand limits exist and they're equal. I think for continuity, it's easiest just to think about where you're discontinuous. So the pictures up above, like the absolute value problem is a perfect one just to keep in mind of what a discontinuity looks like. And you've studied asymptotes in algebra courses, so that one you actually already know about. Okay, the rest of the section, pretty much all graphical, but I want to make sure you have the concepts down so you have a picture in your head when we're doing calculus of what's going on. On to page 27.